Dear colleagues, let me present research cryptographic load sharing method in critical infrastructure sensor networks by authors Emil Faure, Ina Rozlomii, and Sergei Naumenko. The critical infrastructure systems such as energy grids, transformation networks, and medical systems are increasingly relied on sensor networks for real-time monitoring and control. However, the sensor nodes used in the systems have significant limitations: low processing power, minimal memory, and restricted battery life. When traditional centralized encryption methods are applied to such networks, they often overwhelm these constrained devices. This leads to serious consequences: excessive energy consumption, communication delays, and even node or system failures. As illustrated on the slide, the combined effect of high data volume, encryption complexity, and limited resources can destabilize the entire network. Therefore, achieving energy efficient data protection requires a shift from centralized to distributed cryptographic models that adapt dynamically to the energy and computational status for each node. The purpose of this research is to develop a method for efficiently distributing the cryptographic load between the nodes of a sensor network, taking into account the energy state, computing resources, and topological role. The proposed approach ensures optimization of the use of node resources and increases the stability of critical infrastructure networks during encryption operations. To ensure data confidentiality and integrity under constrained node resources, we propose a dynamic distribution model of cryptographic operations. Unlike traditional centralized schemes that cause overload and delays, the model selects optimal nodes for encryption based on energy level, computing capacity, role, and data flow. The architecture presented on this slide illustrates intra-cloud delegation. Unlike the previous architecture diagram, which depicted the general structure of the network, this slide presents a functional diagram of the dynamic delegation of encryption tasks between sensor nodes. In such a system, each node can act as both the initiator and the executor of a cryptographic operation. The process begins with the formation of a request for data protection. The initiator sends a request to neighbors nodes to access the resources. In response, it receives metadata, the level of charge, load, delay, and makes a decision on delegation the task. The selected node receives the message, encrypts it, and returns the result back. Such a dynamic scheme takes into account the current state of each node and allows you to evaluate and distribute the load, avoid overloading individual components, and increase the reliability and energy efficiency of the network. The entire sequence, from the request to encryption and returning the result, is presented in the picture. To implement the model, it's necessary to formalize the criteria used when selection a node to delegate a cryptographic operation. This allows you to adapt the solution to the load conditions, the current state of energy consumption, and the role of the node in the network. The corresponding rules are given in this table. The development of such criteria allows you to flexibility adapt the model to the current state of the network, ensuring both minimizing of energy consumption and increased resiliency to overloads. The method is implemented as a decision-making procedure that uses a set of criteria and weighting factors determined taking into account the energy state, load, and role of the nodes. The process of delegating a cryptographic task is initialized when the initializer node generates a request for data protection. Then the following sequence of actions is performed. The calculation for four candidate nodes is given in this table. The input data was obtained from experimental modeling of the operation conditions of a user network with STM32 microcontrollers, using the typical values of energy parameters and delays. As can be seen from table, the highest value of the integral indicator is for node A, which indicates its priority as the executor of the cryptographic operation in this scenario. In this case, not only the energy resource is taken into account, but also the current load, delays, and the role of the node in the network. This approach ensures adaptability to the real conditions of the sensor network. If the selected node fails, the delegation procedure is reinitialized with the exclusion of the unavailable node, increasing the system's fault tolerance and adaptability. The proposed approach takes into account the role of each node in the topology. The sequence of implementation of the procedure for selecting an executor of a cryptographic task is shown on the slide. The flowchart covers the main stages: request initialization, collection of meta information about the state of the nodes, calculation of the integral utility index, selection of the optimal executor, delegation of the task, and return of the encryption result. To evaluate the model, a test network of STM32 boards was simulated. Eight nodes formed dynamic clusters, exchanging encrypted messages using AES 128 and SCON. Power consumption was measured with INA 219 sensor, and delays were profiled on the microcontrollers. Varying node load and battery levels confirmed the model's adaptability under near real conditions. To assess the effectiveness of the development method, a series of tests were conducted, during which three approaches to delegating cryptographic tasks in a sensor network were compared: centralized encryption on one fixed node, random assignment of the executor among availability nodes, proposed method with dynamic executor selection based on multi-criteria utility function. Each experiment consider of 100 cycles of message encryption of different lengths in a network with active nodes and that had different levels of charge and load. These graphs compare the dynamics of energy consumption, processing time, and the degree of load of nodes, depending on the selected delegation strategy. As can be seen, the proposed model demonstrates the lowest average energy consumption among all options and at the same time provides moderate delay, significantly reducing the peak load on the individual nodes. The proposed method ensures adaptive balancing between data protection and node limitation by considering energy load, latency, and role when selecting an executor. Experiments showed reduced overload on central nodes, improved stability, and extended network lifetime by delegating tasks to less load nodes. The hybrid strategy enables lightweight algorithm use under constraints, lowering energy use without compromising security. Fault tolerance is ensured by reinitializing the procedure or if a node fails. The method is scalable and suitable for decentralized critical infrastructure networks. Thank you for your attention.